Yeah. Or you thought it was vodka or something.
Welcome to the first colloquium of the spring 2019 semester for the Population Studies Center. I'm very happy to have Andrew Bell here today. As it says up there, Andrew's at Sheffield. He's in the Sheffield Methods Institute,
Yeah,
which is
that's
a very
right.
impressive place. He's going to talk to us today about a line of research that you may have seen of his if you read Social Science and Medicine, because he's published there a number of times on it. He also works on stuff many of you might have learned by Paul Allison on random effects and fixed effects models and multi-level and so on. And I found him just a fount of useful and correct information, and that's a rare thing. So I forgot to mention, I mean, Sheffield is a very nice town for you Marxists out there. Recognize it from the writings of Friedrich Engels, but it has made progress since then. And like I say, I'm really impressed by all the work you and your colleagues are doing that's very practical for quantitative methods. So I told Andy, without further ado, most of the time is him, so I'm going to shut up now and welcome Andrew Bell. Thank you.
Thank you. Yeah, thank you for inviting me, and it's really exciting to be here. So I'm going to talk about age period and cohort models. And what I'm going to argue is that actually this is something that often is kind of presented as a niche statistical thing that statisticians argue about among themselves, and most people don't really pay that much attention to. I'm going to argue that if you're interested in any of them, so even if you're just interested in what happens as you get older, age, you need to be thinking about this stuff, and not in the sense that you might find a little bit of bias here and there because all models are wrong and so on. Actually, these can make complete and totally inaccurate inference if you don't think about this sort of stuff properly. So I'm going to start by explaining what age period and cohort are. Hopefully that will be relatively easy. I'll talk about the identification problem. I'm then going to talk about what I've been spending, I guess, a few years kind of doing, which is critiquing a particular solution. So the identification problem has spawned a number of solutions, put in quote marks. And I'm going to talk through one of those, looking at the hierarchical age period cohort model, and explaining the problems with it, I guess, and why those problems exist. At that point, we'll probably all be feeling very depressed because it'll feel like everything's gone. There's nothing that we can do. I'll talk about what we can do, and then I'll give an example looking at mortality. We probably won't have time to get onto the second example, but we can talk about that afterwards if people want to.
Later this afternoon for those.
Perfect, yeah. So what are age period and cohort effects? So the first one of those, age, as you get older, something happens. So here is a woman. As she gets older, she perhaps becomes more likely to die, or more conservative, or richer, or poorer, or something happens that's a result, indirectly usually, of getting older. So that's relatively easy to understand. As we get older, stuff happens to us. Period effects are the effects of things that happen in a particular moment that affect us in that moment, and it affects everyone in that moment. So it might be a medical advancement. Suddenly, we realize that we can solve a disease that previously killed everyone. Suddenly we found a vaccine, we give the vaccine to everyone, and suddenly people don't die of this anymore. Or it might be a recession. During a recession, people become much more likely to be unemployed, and then when the recession ends, that stops being the case. And that affects everyone in that instant. In that instant, there is this period effect, and then people move on to another period, let's say. And finally, we have cohort effects. So cohort effects are the effect of your generation, the effect of, which effectively amounts to the effect of how you were brought up. And that could be quite broadly interpreted, right? You could be brought up. Brought up could mean what happens to you in utero. It could mean what happens to you politically around the age of 15, 16, 18, when you decide perhaps formulate your political views or whatever else. But the idea is that you carry those things with you throughout the rest of your life. So this is something which gives you have your formative years in some way which defines your generation, and that generation then take those attributes on with you, and those again could affect your health, your political views. People coming of age in the Trump administration probably have very different views than people that came of age during the Obama administration, and they're likely to take those things forward with them throughout their lives. Or they might not, and that's something we might be interested in, is the extent to which that happens. So I guess the first thing to say is these three are all potentially real things. They're all potentially real things that exist. We can imagine all of them existing at once, potentially. We can imagine age. Something happens as we get older. We can imagine there being a period effect. We know that when recessions happen, bad things happen, potentially. And we can imagine cohort effects as well. We at least like to think that we're much better than the generations that have come before us, and they in turn will again think that the generations that come after them are also much worse. Some of that is imaginary, but a lot of it isn't. It's very interesting. I saw something from the 1800s of a newspaper article fearing about all of the children that were reading far too many novels, and that this was going to have a disastrous effect on society. But so some of it's imagined, a lot of it potentially isn't. There are things about one's generation which can affect them. So these are all three separate real things, and we can imagine different mechanisms by which these three things could happen, but they are exactly identified. So there's colinearity between these three things. Now, and that's because our age, how old we are, is the year that we're being measured in minus our birth year. And it always will be. And this isn't, now normally when we talk about colinearity, so say we're interested in, I don't know, socioeconomic status and education, and we want to try and find the effects of both of these, but they're quite highly correlated. A solution to that would usually be we'll collect more data, right? We'll collect enough data that we can identify these two effects separately. That's not going to work here because this identification is always going to exist. This identification will always be there. Unless we in some way bring in time machines or bring in some kind of method of some kind of impossible method of disaggregating this, age will always equal period minus cohort. It's equivalent to really putting in, if we were to put into a regression height in feet and height in centimeters, we probably wouldn't be able to identify two effects of those because they're the same thing. Here, these things we've established are different things, but they have the same mathematical relationship. They're still mathematically related in this exact way. What does that mean? Well, let's imagine some data generating processes. So these are three data generating processes, three imaginary worlds that could exist, that could be the truth, I guess. So in the first one, how healthy you are is defined by your age. So there's an effect of age. As you get older, you become more healthy. I'm not saying this is realistic, but whatever. So as you get older, you become more healthy in this imaginary world. Each year that passes, you become more healthy. And as each cohort replaces the next, that cohort is a bit more healthy as well. So you have all of those three effects. In the second example, we've got bigger effects of age and cohort, but no effect of period. And in the third example, we've just got a period effect and no age or cohort effect. So these are all quite different, right? If the thing that you're only interested in is age, these aren't just, slightly different answers. These are not being an effect or a really big effect or a medium effect. But if we look at the data produced by these data generating processes, these three data sets will be exactly the same. They won't just be kind of similar, they will be exactly the same. The numbers that come out will be exactly the same. And so that's kind of the point to think about when people say that they've solved the identification problem. What they're really saying is I can tell three data sets that are exactly the same apart. So this is the level of kind of questioning that we need to be thinking about. That particularly with linear effects here, there's going to be a problem in separating these things. So the key thing here is that there's an experimental problem, really. We can't hold one of these things, can't change one of these things whilst holding the other two constant, at least without using time travel or something like that. We can't do that. If we hold age and cohort constant, we're by definition holding period constant. So there's no kind of experimental mechanism, no causal kind of counterfactual that actually makes sense in this sense. So this is why Norval Glenn describes this as one of the most bizarre instances in the history of science of repeated attempts to do something that is logically impossible. But people keep trying to solve this problem. People keep coming up with new methods that have solved this, that kind of provide a new answer to this problem. And the key thing here is that even if you only care about one of these, if you only care about age, you might think, oh, I only care about age, I'll just ignore period and cohort. But the data's still been generated this way, whether period and cohort are in your model or not, they're probably in the data. And certainly if you have any of them in your model, you've probably effectively got the others as well. So it's worth being aware of exactly what's the problem here and what isn't. So for the moment, all of these have been linear effects, right? So a linear effect of age, a linear effect of period, a linear effect of cohort. This only, for the most part, applies to linear terms. So non-linearities can be identified, and usually are identified in the same way, with some caveats around it, situations where you could plausibly have find that not happening. For the moment, we'll say that non-linear things are identified. So we can find, in theory, using regression, we can find a non-linear effect of age, period, or cohort. But what this means will depend a lot on what the linear terms are. So if we think about these three imaginary worlds, they're the same as the last ones, except I've added in a squared term of negative 0.1 for age squared. So in these examples, these three data sets again are going to be exactly the same, but in each of them we're finding the same and probably correct age squared term. But what that age squared term means is going to be very different depending on what the linear term is. So in this example, we're probably going to have an inverse U shape, whereas in this example, the effect of age is actually a linear term with a bit of a curve in it. They're very different things. They mean very different things substantively. So how useful that is will depend on the research question, but to some extent could be not that useful at all. I should say, by the way, if anyone wants to ask questions as we go through, feel free. I will. So at this point, it's worth, I guess, thinking back to when I was doing my master's before I did my PhD. And I came across this model and thought, at that point, this is amazing, this is great, this can solve this problem. And it was presented as a solution to this, and it basically used a multi-level model, or a hierarchical model, in order to, in some way, separate these three terms out so that the model could provide estimates of all three. And I did it using a cross-classified multi-level model that looks something like this. So we have individuals nested within the year they're being measured in and their birth cohort. And these models were designed for repeated cross-sectional data. You could use panel data as well. You'd have to add another individual level to it, but the logic of it's the same. So you have multiple cross-sections over time, people of all ages or cohorts in that data set. And you estimate the effects of the year and of the cohort group, the birth year, as random effects. So these are estimated as random effects. And then age is estimated as a fixed effect, a fixed parameter, as a polynomial in the fixed part of the model. So in your model, say your y variable is health, you've got your age trend represented by a polynomial of some kind. And then period and cohort are represented as random effects in the random part of the model. And this was billed as a solution to this problem. So there's a lot of quotes here saying that this model has resolved the identification problem. It's no longer a problem. It doesn't incur this problem. A lot of quite strong language here suggesting if you're someone that wanting to use it, like I was when I was doing my master's, this is the solution. This is perfect. I found an answer. And the more that I got into this, so I did my master's, I used the model, got some results, didn't publish it, fortunately, then looked a bit further into it, and then started to think, hang on, there's something that's missing here. There's something that's not working. So I did some simulations to see what happened to this model when different conditions were put onto it. So for one of these papers, I used one of the published examples that had used this. So there's a paper by Reiter et al. Published in 2009 in Social Science and Medicine. They were looking at obesity. And so they found this these right-hand graphs. So they found that as you get older, so this is the age effect, there's this kind of inverse U shape. As you get older, you become more likely to be obese and then less likely to be obese in old age. They found not much going on with cohorts. There isn't really much of a cohort effect there, a bit happening at the end, but not really. Really the thing that has produced what you might call the obesity epidemic, this is American data, so the obesity epidemic is driven by year rather than cohort, okay, according to their results. And that kind of matters, because if you're interested in solving the obesity crisis and you're thinking, who do we need to target? If this is all driven by cohort, you might say, actually, once you've got through your formative years, the things that define you as a generation, there's not much point in targeting you. There's nothing that can really change. We need to maybe target children or target people in their formative years. Whereas if you believe this, you might think, actually, people are more malleable. People can change as a result of years passing. Something about years that leads people to be more likely to engage in unhealthy behavior. So this does kind of matter, even from a policy perspective. So what we did was we generated some data that looked a bit different. So we generated data where the obesity epidemic was really being driven by cohort replacement, changes in cohort, differences between generations, rather than periods. So there's not really at least a linear or at least a continuous period effect. And then there's a bigger age effect there as well. So we used this data, put it into the hierarchical age period cohort model, and these are the results that came out. So we were able to, it's a kind of weird backwards replication where replicating isn't good news for the authors. We were able to replicate the results using data that we knew was not true, or that we knew was different to what had been found by the model. The implication being that either of these two patterns could have produced these results. So the results don't really tell us enough. They don't actually tell us what the authors claim that they do. These results could have been produced by a cohort effect. So a debate kind of followed from this. So we wrote this paper in 2014. The response, so they then responded. They said, you know, this is unrealistic. You're using simulated data. The simulated data, this obviously works with real life data, which is, you know, convenient given that you can't test what's happening in real life. So they said, but they then said, you know, but it works on this simulated data set. It's like, there's a logical issue there, but okay. We then swapped some things around in their data, found that it didn't work with that. They then respond, oh, of course it doesn't work with that example. That clearly that won't work. So there's been some shifting of goalposts happening throughout this debate that's kind of gone on. And I imagine we'll keep going on. We'll see whether they respond to the latest one. So I guess there's an interesting question about, you know, how science progresses and whether this is particularly constructive. But you can have a read of that debate that happened in social science and medicine. This kind of led me to think, though, about a few questions around this model, particularly why it finds what it finds. So we worked out that sometimes it finds the wrong answer, but we hadn't really worked out why it finds the results that it finds, right? And what we came up with was the idea that this is actually something that comes down to the structure of the data that we're using. So with pretty much all studies that use this method, the structure of the data looks something like this. So we have repeated cross-sectional or panel data that would be give us a rectangle in an age by year diagram. So these arrows represents a cohort kind of traveling through time, I guess. They're measured in multiple occasions, getting older each time as they do it. And so this is what panel data usually looks like, or repeated cross-sectional data would look like that, except that the individuals wouldn't be followed through if it was repeated cross-sectional. So we could arrange that like that, or we could arrange it by cohorts as well, effectively just shifting everything across, making it look something like that. But that's not the only way that data could be collected. It could, instead of being collected by years, by panels, or by cross-sections, it could be created by cohorts. So at least in the UK, there are a number of cohort studies, one in 1946, one in 50-something, 58, I think, one in 1970, then Thatcher happened in the 80s, and then they brought it back in year 2000. So basically, the idea of these cohort studies was you take a group of people, all of whom were born in the same week, and you follow them for the rest of their lives. So you follow them on multiple occasions over time. So that's an individual born at a particular time, and you then follow them through their lives. If we were to arrange it by year, it would look something like this. Actually, I think possibly it should be turned the other way. I'm not quite sure. But the key thing here is that this data is collected by cohorts, by birth years, by birth occasions, rather than by years. What does this mean in terms of the modeling? Well, we're interested in knowing where, effectively, linear or near-linear effects end up going. And in the hierarchical age period cohort model, if there's something that changes over time, it needs to go in either the cohort residual or the period residual. Those are the ones that kind of measure change over time from a society point of view. And so if we have a linear effect of, say, strength 1, like in those imaginary data generating processes, and we want to know where to put it, the model is in some way needing to decide whether to put it on cohorts or periods. And if it puts it on cohorts with in panel data or repeated cross-sectional data, that's going to produce outcomes that are from a very wide range of cohorts, right? The range of cohorts in a panel study is much bigger than the range of years. Taking something like the British Household Panel Survey, that runs from 1991 to 2008, so it's 18 years that is the range of years. But the cohort range is much bigger. The cohort range will go from people that are, let's say, 70 in 1990. They're going to have been born in the 1920s. Doing some maths in my head there. Going all the way through to people that are young in 2008, probably born around 1990. That's a big range, a much bigger range than the 18 years of the periods. And so if we're going to put a linear trend on one of these, if we put it on periods, the range that is going to be produced is going to be much smaller than if we put it on cohorts. Now, in a multi-level model, when we're looking at those random effects, the model penalizes big residuals. In fact, most models, you're looking to try and minimize your residuals, right? Even a linear regression, you're trying to minimize your residuals. That's what the model does. And the same applies at the higher levels as well. And so if the model is trying to think how to minimize the residuals, and it can choose between these residuals that are really big or these residuals that are really small, it's probably going to choose the one that's really small, right? So it will tend towards periods rather than cohorts. And the key thing about this is that this is nothing to do with any substantive process that's happening. This isn't anything to do with the actual processes that produce obesity or anything like that. It's just to do with the data structure. And if we'd collected the data by cohorts, the implication is that we'd have got different results. And so we tested this in a number of ways. So firstly, we tested it with simulations. So we ran some data simulations where the data was generated in these two different ways. So we created a data set that looked like that and a data set that looked like that. Gave them the same age period cohort data generating processes. And the results that came out looked quite different. So you can see that the black lines, the black dots represent the truth, in this case, the data generating process. And you can see that whether on the top, I think, I can't remember which way around it is now, I guess, probably there's a cohort trend there. So this will be the data generated by cohorts. This will be the data generated by periods. And you can see the truth, which is the little lines here, 100 iterations of each. The truth is is different depending on which one you choose. But kind of following Yang and Lan's claim that actually you can't really test this with simulations, I was trying to think of a way in which we could do this with real data as well. So is there a way that we can do this using real data? And if I was able to get a huge amount of money and a load of time to run lots and lots of cohort studies across what would have to be a number of probably hundreds of years, I'll be able to test this. Unfortunately, that's quite difficult to do. So what I did instead was took a data set that did exist, a repeated cross-sectional data set, actually the same data set that was used in that Reiter et al. Paper, and I cut it up, basically. So I cut it up, and if you look at the black boxes, they kind of show how I cut this data up. So I took 6, I guess, samples from this data. So we've got age along the x-axis, year along the age along the y-axis, year along the x-axis. I took a sample that basically would produce a sample where there were more years than cohorts. So I took a narrow sample of cohorts and just looked at that group of cohorts and got rid of the rest of the data. Did that on a number of sections of this data to see if the results would be different using this real data, but using a particular sample that was cut from it. And these are the results that we found, and indeed the results are very different looking at these 2 different examples. So when we selected the data by age, so the colored boxes, I just took a chunk of age just to kind of see how that would look. And the results were very similar to those produced by the Reiter et al. Paper. You can see that you've got that, if you add these trends together, you've got that inverse U shape of age, that linear trend of year, and then not much happening with cohorts. But if we select the data by cohort, so these are the 6, the data from the 6 boxes, you can see that we actually found the opposite. So we found a bigger age effect, again, nothing much happening with year, and then a change happening as a result of cohort instead. Which I can't see any reason why that would happen other than the logic that I guess I've just described. I can't think of a reason why that would have happened because of the real data. Yeah. So the key point here is we've tested this now with simulation. We've tested it with real data. And it seems there's something wrong with this model. And indeed, of course, we know that there must be something wrong with this model, right? Because we know from the beginning that we can't tell apart different data sets. And this is one example, one model that has been used fairly widely in the social sciences. There are others. So there's one called the intrinsic estimator. Partial least squares estimation has been used in epidemiology a bit. And in each case, either they haven't really been robustly tested with simulations, or they have been tested and they've been shown not to work. So these, and like I said, we know that they can't work when there are linear trends or near linear trends in the data set. So far this is all fairly depressing. So far we're thinking, okay, we might as well pack up and go home. We're never going to be able to find an answer to this. And I think there's some argument in favor of that, but I think also there are still some things that we can do. So we can think about nonlinearities. Remember that we can still identify these. It's often difficult to know what they mean without the linear trends included, but we can find them, and in some cases, we'll see in the example, in some cases this can be useful, it can be meaningful. The other option that we can do is make some kind of big assumption. And throughout the literature, there have been various attempts to try and make an assumption that seems quite small so that you don't need to actually worry about things too much, right? So a lot of people will group two sets of cohorts together and say, that's a pretty small assumption. They're next to each other. They're going to be pretty similar. We'll just do that. And then our results will be correct. But that assumption, the model results will be very sensitive to that assumption. It's much better to make a really big assumption. Something like, I think that period effect will be 0, or I know that the linear term associated with age is 0.6, or something like that. You need to constrain one of these linear terms to a particular value, and then go forward. And then if that assumption is true, you can then be confident that the other results that are produced from this model are also true. But it's a big assumption. It's going to be a huge assumption. If the assumption is of something that actually you really want to are trying to find out, then that's not going to be particularly useful. I reviewed a paper recently, actually, that approximately the argument was we've made an assumption that cohorts look effects of this size, and we found that cohort effects of this size. Isn't that interesting? Not really. That's not particularly useful. So we need to think about what our question is, what we can really say. But what I will say is that probably an explicit and honest assumption that is entirely unjustified is much better than pretending you're not making any assumption at all. Because actually, these models are making assumptions. It's just they don't tell you what those assumptions are and kind of pretend that there isn't one. It's much better to come up with some assumption, any assumption, make an argument for it, because then at least people can respond to it. People can talk through, and science can progress by I guess, debating those assumptions. So, yeah.
Isn't this reminds me of my 6th graders math problem set, where don't you by construction have to have a constant to have a solution, to have a solution? I mean, when you have this perfect, you have to create some constant, otherwise there's no mathematical solution, right?
Exactly, yeah. So you have to, and that's effectively what you are doing in this. So this is what this assumption is. You have to make some kind of assumption. So there's been, so back in, I guess in I think probably the 70s or the 80s, people were kind of thinking about how to solve this, and they, so if you were including all these variables as discrete kind of categorical variables, I guess, people would say, oh, we'll just say that people that are 15 are the same as people that are 20. That seems pretty reasonable. Or even better, people that are 65 are the same as people that are 70. So that's your assumption. That's your constant. Right? That's your constraint. The problem is that has often unpredictable effects on what the ending result is going to be. So I guess there's two questions. One is the mathematical question: how can we get this bloody model to give us an answer? And then the second question is that answer going to be in any way meaningful? And so I think you kind of need both, right, for there to be any point. Yeah. Okay, so I'm going to talk through an example of this. This is kind of work that's still in progress, so if you have feedback, let me know. So looking at mortality in the across rich countries, using data from mortality, the human mortality database. So we have data on a number of countries on mortality rates for all age groups across a number of years, basically. So pretty much throughout the whole of the 20th century for a lot of countries. And so we were interested in using this data to try and find specifically discrete effects caused by specific events throughout the 20th century. So that's important, the fact that we're interested in discrete changes. So things like, what did World War I do to mortality of people? What did World War II do? What did the Spanish flu do to people? And there's a strong literature that will, firstly, we can see why there would be period effects of this. Wars happen, people die, right? The chance of you dying is much higher in a war than not. if you're alive during the Spanish flu, probably you're more likely to die than in another year. But there's also a strong argument that there would be generational effects as well. So this is things like, a lot of these arguments come from epidemiology and the ideas of a life course perspective, that as you go through life, you take on, I guess, issues that you then carry on through your life. So there may be health issues, potentially in utero, that you then can take with you throughout the life. And so the key thing here is that we're not interested in more long-run changes. So we're not interested in how your mortality improves as you get older. We know that, or gets worse as you get older. We know that as you get older, you'll become more likely to die. We also know that as time went through the 20th century, mortality rates declined gradually over that time. Again, we're not particularly looking at that. We're more interested in what these kind of specific events, these discrete occasions do and what they do from a point of view of periods and cohorts. And this is explicitly exploratory. So we're kind of looking to see what the patterns are. We're not really testing hypotheses here. And so I think I've already kind of talked about this, just to say there's a literature behind the idea that there would be cohort effects in these sorts of events, like the Spanish flu. Some other kind of classic examples in the epidemiological literature has shown people born around the siege of Leningrad in the Dutch hunger winter were at higher risk for various diseases, various problems. The key idea here is that our early life experiences are hugely important to what happens next. And so we fit a version of the hierarchical age period cohort model to this data. There are a few differences. So the first, I guess, which I'm going to gloss over, is that we're using a Poisson model here. So we're using the number of deaths as our Y variable. We're using an offset of the expected number of deaths, which effectively means that we're modeling the mortality rate. So that effectively means we're modeling the rate. You could use a logit model, and the results are pretty much the same if you do. And then just like before, we've got this structure of there being, I guess it's kind of an individual, but really it's a cell in our data set, looking at the number of deaths in that age by year cell. And they're nested in years, and they're nested in cohorts. And then just like before, we've got age in the fixed part of the model. But now we've also added period into the fixed part of the model. And if we were going to interpret these, we would be effectively assuming that there are no cohort trends in this data. But we're not going to look at them because we're not going to make that assumption, and because we're not actually that interested. The key thing about this fixed part is that it's getting rid of age and period and cohort linear trends from these residual terms. So these residual terms will effectively be free of these linear trends. We'll only have the nonlinearities left. So yeah, like I said, it's data from the human mortality database. We ran these models in R, calling MLWin, which is another software package, because we couldn't make it work in R's home things. So they're run using MCMC. And so these are the results. Sorry that the numbers are kind of small. So this is looking at the results for the UK. We've got year along the x-axis, and we've got effectively the size of the period level residual on the y-axis. So really higher values mean higher mortality. And so the first thing to say is you can see this non-linearity kind of sweeping through here. And actually I kind of want you to ignore that, because these are non-linearities that are effectively left over from these linear trends, whatever they are. And so what they really mean, it could be that there's no linear trend in this and these are accurate. It could be that actually these are just slight departures from a linear trend. So I think don't interpret those particularly. What's more useful here are kind of discrete differences, so jumps in mortality that happen. The key one being here, World War II, there's a big jump in mortality around those years. associated with a period effect at that time. And then these are the results from cohort, and you can see again this long-run nonlinearity that I don't want you to interpret and don't want you to particularly look at. And again, the things that we're more interested in are these non-linear kind of sudden discrete occasions. So the Spanish flu happened in 1919, and you can see there was a big shock. So people born in that year, people who are born around that time, have worse health outcomes and are more likely to die, the implication being throughout the rest of their lives as time goes by later on. Even today, people born, if there are any still alive, people born then have a higher mortality rate than you would otherwise expect. I guess they'd be 100 years old now. I mean, at that point, maybe there's an argument that they're probably all right, but yeah, absolutely. And then also you can see here that there's a fairly significant drop in mortality there associated with 1948. We were really excited when we found this because 1948 is the year the NHS was formed in the UK. So we thought, that's going to be a good story. We can sell this. And then we found it in some other countries as well, which rather ruined our hope. So to be honest, we don't know exactly what it is that caused that. I don't know where there are a lot of kind of things happening around that time relating to public health and public services and things like that, not just in the UK, but in a number of countries post-war. They didn't all happen in 1948, so it's a bit unclear why we'd have found just that effect happening kind of discreetly there. So if anyone has any ideas, let me know. Or there might be something to do with the way that the data is in some way imputed or something like that that might have produced that result. So I'll be interested to hear what people think. It's worth saying, so this is a, no, that's fine. This is a Lexis diagram kind of showing the same data for the UK. And it kind of shows, I guess, visually the same things that we've been seeing in that graph. So you can see firstly, kind of the way to, so you've got year along the bottom, year along the x-axis, year along the horizontal axis, age along the y-axis. In this graph, red represents a change of mortality. So it means if there's a red dot, that means that mortality has gone up for people of that age compared to the year before. And so there's various patterns you can see in this. You can see some of those period effects, which you can think of as these vertical lines. These are period effects. You can see Spanish flu and the war happening there. You can see the difference between men and women. So the men going off to war, particularly around the age of 20 to, looks like about 35. And you can also see cohort effects. So the cohort effects are the kind of coming from the birth year and carrying on through the lives. So this is 1919. You can see this is those people, even up to 90-year-olds, it seems actually there is still a higher rate of mortality compared to 100-year-olds, or well, it only goes up to 90, but compared to 90-year-olds in the previous year, there does seem to still be something left over in there, which is kind of surprising and kind of interesting.
Just to clarify, this is still net of the linear trend, right?
So because we're looking at change rather than absolute kind of mortality, yeah, effectively. Yeah.
So I guess, isn't it surprising? So there's, the 1918 flu epidemic produced a cohort effect. But in some ways it's striking that this is also the main leading candidate across the 20th century, if I look at this.
Yeah.
And so, if, given how you introduced this early on, we think there are these distinct cohort effects and all these different periods growing up at different time and having these down. And then, if I look at this graph and it says, well, across the 20th century, the one cohort where people agree there's a cohort effect was really bad to be in uterus during the epidemic. But through most of the 20th century, it's not clear there's any kind of cohort effect standing,
Yeah, I mean,
jumps to your eyes here.
I agree, and I think that I was expecting to find more based on things like World War I, World War II. it's interesting that there isn't, well, okay, I mean, the flu epidemic, it's to some extent difficult to separate from the World War effects. But yeah, I would have expected to see more associated with war. I guess there's potentially you could imagine maybe people would be affected in different ways by these things. So you could imagine a war, growing up during a war, really toughening some people up, and then they're good for the rest of their lives. Other people get broken by it, and then they really struggle through their lives. Maybe they're cancelling each other out. I don't know. I'm speculating somewhat, but you're right that there perhaps isn't as much as you might expect. Yeah. Yeah.
Their previous, what the Marshall Plan, 48 when they started.
Yeah.
The U.S. started dropping food all over Europe.
It could be. That's a thought. Yeah, I don't know. I'll need to look in. Yeah, so that was on the list of possibles as example. It still doesn't quite explain why it happens in lots of countries. I'm trying to think where else. I can't remember which countries we found it in and which we didn't, but it was a number of countries. I think it included the US as one of the countries that this affected. Well, either US or Canada. I need to check, but yeah, I'll work out if that kind of makes sense as well. Yeah.
Would there also be some selection effect in the sense that the greater people would have died during the war and aftermath, and so then
yes.
that could be sort of a selection effect.
Yeah, but again, I'm not sure why that would be specific to 1948, really, unless there was some big return of people from around then, but I would have thought they'd have been back by then. So, yeah, we thought about all these. Someone suggested the invention of penicillin as a potential, which was kind of gradually introduced, but around that time. But again, not really specific to 1948, so it doesn't quite explain it either. Yeah.
Are you allowing your parameters to change a long time? Just going back to the model.
How do you mean
Because if there is a war or there is something very different, then one could imagine that maybe the methods could be changing across time.
Yeah. So these are. So all of these are allowed to they're random effects, so they're allowed to be different from one another. Is that what you mean?
Yeah, maybe it's just that the model to me is not completely clear, but.
Yeah, well, the model is very much imperfect, I think. Partly because we've got fixed effects that we know are probably wrong. We've still got these curvatures in this random effect, which kind of break our modeling assumptions in various ways. So you're absolutely right that there are issues around that. I think it still tells us something useful. I think it's still the fact that we're seeing these patterns appearing at least makes us stop and think about why specifically that these things might exist. So I think we're allowing for there to be differences across these years. Yeah.
So you raised something that always has bothered me. You mentioned in the random effects case, because one is claiming these things are random effects, then it's somewhat bothersome that you get. But even in the case where they're fixed effects, if you weren't doing a multi-level and you had some, in some ways the hierarchical thing is really relevant. It's always bothered me that, in other words, whatever you're looking at there has to be uncorrelated with trend, by definition. Yeah. So it always comes out looking like that. There's always something that, and I start thinking about how much of that is in the structure of data and so on. One of the things that I'd be interested in what you think, but in one of Holford's, I think, his earliest main paper on he identifies by assuming there's a zero linear period effect. He didn't really explain, he just kind of does it. His math, and then But then when he starts reading the data, because of course there is some pattern in what he starts projecting, like downward off of the thing.
Right, yeah.
And so I'm trying to come to a question here. I mean, to what extent does the identification assumption, should it or should it not guide us from reading too much into any kind of other nonlinear trend of this thing that's been generated under the assumption that there is no linear trend?
Yeah, so I mean, taking this example, am I allowed to draw on this board? That's right, yeah. So we've got something that looks something like that at the moment. But you could, so if there actually was a linear trend attached to this, let's say that there was a general downward trend attached to it, it would probably look kind of, I mean, it might even look, basically linear, yeah? And so if you're using this and thinking, oh, well, that's fine, it's just going to carry on, that's equivalent to saying it's going to carry on going down steeply, right? So, yeah, it's something that I think if you are predicting it in that way and thinking, or even worse, I guess, if you had something like that and then you decide that that's what's going to happen next, then that's
a little what's in that Holford.
Yeah, well, that sounds, I don't remember the Holford paper, but it's I agree that would be, especially when, as you say, your identifying assumption is saying that that's not going to happen. Yeah. Yeah.
You might go back to your slide. Sorry, I really interrupted you.
No, that's fine. No, it's all right. Keep going.
Back to your slide, we have the Riker 2 simulations next to each other.
Was that
where you find these different shapes? Yeah.
that one?
No, forward to more.
That one. Yeah.
Yeah. So this sort of makes sense to me if you have this hierarchical model where all of your random effects are normal IID random effects. But can you assume, and you talked about, if we just had some constant instead of a normal IID random effect, then we can identify it. But could you also impose some sort of more complex functional form on either age or period cohort random effect rather than just having it feeling this totally uninformed normal IID random effect? For age, it's probably the safest to assume compared to period or cohort that there's some functional underlying form there.
Yeah.
If you had some sort of Gompertz distribution on that random effect instead of having it just be totally uninformed.
Yeah. So I mean, if you know kind of the medical reasons why people become obese and don't, over time as people age, you can absolutely, that could be your assumption. I don't see why not at all. I guess within that assumption, there is going to be some kind of linear component, I guess. And even if you aren't thinking of it as a linear component, there's going to be something that is going to lead other linear components, if they exist, to operate in certain ways. So the answer is yes, but not in the sense of it being particularly any more likely to be informed or any more likely to be unproblematic, I guess, if you get it wrong. I'll quickly finish off, and then we can go into proper questions. I'll skip through example 2. So just, I guess, to sum up, I guess the key thing here is that age, period, and cohort are important. They matter, and we need to think about the identification problem. It's, I think, very and a lot of people do this where they say, oh, age period, that's something that's too difficult for me to deal with. I'll just put age in the model, it'll be fine. It doesn't help. The identification problem is still there, and so we need to take it seriously, acknowledge the problems of it, and then come up with some kind of solution. And that involves usually making explicit assumptions or being honest about what we are and aren't doing. So if we're only interested in those non-linearities, that's fine, but what about the other types of non-linearity that really mean something different in other things? But if we're willing to make those assumptions, if we're willing to be honest about these sorts of things, I think that these models can be powerful in various ways throughout social science. And that's pretty much it. So thank you for listening. Yes.
Yeah, I think that was a super clear presentation of like the different pitfalls and like processes. So that was very helpful. And what I'm wondering is about bridging how we conceptually and theoretically think about the three effects and how we model them. And with the hierarchical solution, there's this assumption that age will be fixed. Like we don't think about how age operates across different years as different. And I was just, you know, and if it's only about 1 year, one cohort in which the age operates differently, we think about that as a cohort, but we could think almost as a transformation, like a period kind of transformation in how age operates for like all the following cohorts, like something like a medical advancement potentially or something like that. And how, yeah, so like how the idea that age will operate in a fixed way across time is maybe a little bit foundational of these models, and maybe how that assumption even could be shaken up.
Yeah, I mean, so for me, that assumption is kind of logical in a way, in that there's no reason to think that something specific would happen at the age of 27 that would make your mortality suddenly go down and then go up again by the age of 28. You know, in general, you would see a smoother shape, I guess, in age than you might with cohort and period. So you know, that logic of the hierarchical age period cohort model, to some extent, is why I was intuitively drawn to it. The idea that periods and cohorts are contexts in which we exist, whereas age is something that's more internal, that is, I guess, more fixed, I sense. But yeah, I think if there was, you could imagine at least possible examples where there would be, could be a particular thing happening around certain age events, around retirement potentially, or around specific life events that are associated with particular ages, for sure. Yeah.
No, I think it's. I have a broader question, and you know, what would you say to people like me who think that this is logically impossible to solve, and that these, you know, sort of exercises are just, you know, and you know, and I think that what's the role of theory and statistical? It seems to me that this is really a problem with the theory in terms of how we look at how we interpret these things, and then it doesn't matter what we do statistically. This is logically impossible to solve unless you know, unless there's something wrong. You know, can you go back to your first initial?
If I go, say when.
The first simulation that you did of a published paper.
That one?
This one.
Yeah.
So, you know, my understanding is that they found the 2009 found those coefficients, and you know, your interpretation was that we find period effects, we can make it fluctuate. But that's not what that's not the finding. The finding is that, you know, it keeps increasing over time, and there actually, you know, the period effect is that it keeps increasing, and so, you know, and then the other simulation, you know, it actually shows that it keeps increasing over time in terms of cohort, that if the period effect fluctuates very little. So I actually think that you have the same conceptually. So at the end of the day, it seems to me that you know, it's a logically impossible problem to solve that should point us back to thinking about theory when we interpret the results of our models, and not, you know, trying to separate effect of this or effect of that.
Yeah, so I mean, certainly the first part of what you said, I completely agree. So yeah, yes, it's logically impossible. Yes, we need to bring theory in. Yes, I think the bits where I disagree with you is that, think about these age effects. These are conceptually very different things, right? So how we are, which of these, even if we just say it changes over time, whatever, which, you know, that kind of makes sense, I understand that. How we think that it changes over time is going to affect the results that we find for other things that we think of as actually, you know, more meaningful, perhaps. So I don't know if you know Harvey Goldstein, who's at Bristol. He's done a lot. He's kind of developed a lot of the multi-level modeling stuff. I had so I dug this out, a paper from the 70s that he wrote, basically saying this is something that is logically, not just logically impossible, but it's a question that doesn't make sense. So his argument is, I think like you're saying, yeah, that actually there aren't three things, right? There are just two things. So I guess there's two ways of arguing against that. The first is, okay, there's two things, but what are the two things? Which two, right? And that's a question. Because, which two you decide affect the results that you get. And the other is that we kind of can imagine all three of these things existing, right? So all three of these things do, to some extent, we can think about ways in which all three of them do exist independently. I think part of where this comes in is so normally when we're talking about finding effects, we're in some way thinking about a counterfactual that could exist. And in our case, that counterfactual can't exist because if we're looking at the counterfactual effect of one of these variables, we have to be changing the other ones. So from that perspective, if you see that perspective, you're saying actually there's no, what are we doing? There's no effects here. My argument is that actually these effects can exist even if they can't be, even if the counterfactual can't exist. Just like if we have, if we are, let's say, running a race and there's a wind blowing and we're quite strong, so we run quite fast. These things are, we end up with just a time. There's only one of me and we haven't changed the conditions at all. That doesn't mean that the fact that I'm quite good at running and the fact that the wind is blowing aren't both affecting me. There's still multiple things affecting me, even though in the data there's only one dimension. So I think there's something similar happening, right? That I think all three do exist, but I completely agree that we can't solve the problems without theory and without trying to come up with some kind of reasonable argument as to why we think actually one of these is kind of implausible potentially. So maybe we say, actually, how does cultural change really happen? What is it that leads people to do less exercise, eat more hamburgers? Is it something that's learned in early life? Is it something that are people just going through life and actually, because there are more McDonald's adverts now, everyone's eating more McDonald's? Might be. To be honest, I don't know the answer to that. But as you said, it's a theoretical question and a theoretical thing that needs to be developed rather than some kind of statistical trickery, I guess.
Listen, everybody, this is great, Andy. We'll hear more from you at 5. And Amelia, show up and I'll argue again.
Thank you.